Hello everyone and welcome to this video. So what I want to do in this video is deal with the Laplace transform. Now bear in mind that this will not so much be teaching the Laplace transform because it is assumed that you already do have some knowledge about Laplace transform. So this will be more of a refresher, more of a reminder on what the Laplace transform is and how we compute the Laplace transform. So we will just simply work by taking an example. If I can get my pen to work. Okay, so let's take an example. Let's say, or first of all, let's talk about the definition of the Laplace transform. Now, usually the Laplace transform, we write Laplace by something that looks like a squiggly, something like this. And so let's say we want to find the Laplace transform of a certain function t. Then we would write it something of this nature. Now, to make our life a lot easier, usually we use the uppercase of the function name, and then we make it a function of s. You could just remember that s is really defined as, f really is defined as alpha plus j omega, and I won't go too much into this, just to mention that omega is your frequency, but I won't go too much into this definition right now. So this is to find the Laplace transform of f of t, and sorry, my pens are frozen once again. Okay, and now this is defined as, we take the integral from 0. Now strictly speaking, we call it 0 minus, in other words, just before time t is equal to 0, of the function of t multiplied by e to the power of minus st, where s is defined as alpha plus j omega, and we integrate this with respect to time. So this is the definition. Usually we don't bother writing this negative all the time. This negative over here, we just write 0 to infinity. So this is the definition of the Laplace transform, and you can simply use this integral to compute the Laplace transform at any point in time. But let's just take an example, if you want, the simplest example that we could have. Let's say we wanted to find the Laplace transform of a constant. So we want to find the Laplace transform of 1. So to find Laplace transform of 1, that's where integrating from 0 to infinity. Our function in this case is 1 multiplied by e to the power of minus st dt. Okay, so obviously this is just the integral of st dt. When you integrate e to the power of minus st, what you have is minus 1 over s e to the power of minus st, and we're taking this from 0 to infinity. Remember, limit of integration, because this is a definite integral, so we're going from 0 to infinity. Now I should mention that once we're finding Laplace transform, generally we would always assume that the function that we are finding Laplace transform of has 0 initial conditions, or if you want, its value is 0 at time t is less than 0. Okay, so it's just good to bear that in mind. Okay, so let's slot in infinity into these parameters here. So this is equal to negative 1 over s into e to the power of minus infinity times s, which is just simply minus infinity, negative minus e to the power of minus 0, if you think the negative there is necessary. Okay, so e to the power of minus infinity, that's 1 over e to the power of infinity. E to the power of infinity obviously is infinite. 1 over infinity, well, we take that as 0 in mathematics typically. Well, actually we should say the limit as whatever parameter goes to infinity. Okay, so it's actually more accurate, if you want, to write this as the limit as, say, let's say x, as x tends towards infinity, of minus 1 over s integral of e to the power of minus x minus e to the power of 0. I'll drop that negative sign because minus 0 is the same thing as 0. Okay, so this is actually what we're finding when we try to compute this, and actually this integral is the same thing as the integral of the limit from 0 to x, instead of taking from 0 to t. So maybe I should actually leave out this expression I just wrote here, because this is rather confusing. What I should have done is, instead of finding this integral here, I should have found the integral from 0 to x of 1 times e to the power of Okay, so now let's back up just a little. I shall find the integral from 0 to x of the limit as x tends towards infinity of 1 times e to the power of minus st dt. Actually, we could take the limit out of this integral. It's effectively the same thing, so the limit actually should be outside. So the limit as x tends towards infinity of the integral. So let me just go ahead and rewrite that in the appropriate way. Okay, so this should be the limit as x tends towards infinity of the integral from 0 to x of 1 multiplied by e to the power of minus st dt. So this is actually what we should have done instead of going through this route, but then we can also just take this route and we effectively I'll just leave it be as that. Okay, so let's just assume that this doesn't exist over here. I should probably erase it, but I'll just leave it there since I wrote it a little earlier. So this will be equal to minus 1 over s, and I'll say e to the power of negative infinity is simply equal to 0. Okay, that's 1 over infinity, which is 0. Then minus 1. E to the power of 0 is 1. Okay, so what we have inside this bracket is simply negative 1. In other words, this is 1 over s. So let's write that out again. So we're saying that the Laplace transform of 1 is simply equal to 1 over s. Okay, so that works. Let's pick another example. Let's say we want to find the Laplace transform of, again, another simple example, e to the power of a t. Okay, so this is a function of time. We want to find the Laplace transform of this. So the Laplace transform of this is, if you want, I could write it in this form, but let me just go ahead and write it straight up as an integral. Bear in mind that in reality what we're doing is finding the limit as x tends towards infinity. So e to the power of our function is e to the power of at. We multiply that. Okay, let me put a negative sign here to make it as easy as possible. Okay, so a negative sign there, e to the power of minus st and dt. Okay, now our the parameter, the functions that we're integrating, we can also combine them together since they are both exponentials. That's e to the power minus at, e to the power minus st. Let's combine these together. That's e to the power of negative into s plus a multiplied by t. Neither a nor s is a function of t, so this comes out beautifully as being minus 1 over s plus a multiplied by e to the power of minus s plus a multiplied by t, limit of integral from 0 to infinity. Now if we just scroll up just a little bit, we see that when we had a function that was very similar to this, when we had this expression over here, okay, when we had this expression over here, it just simply turned out being 1 over this coefficient you have, the positive of this coefficient you have over here. So I could save us some time and just simply say this is equal to 1 over s plus a. So when our function of time is simply 1, the Laplace transform is 1 over s. When the our function is e to the power of at, that's e to the power of minus at, don't forget the negative sign in the power, e to the power of minus at, then what we have is 1 over s plus a. Now let's take the other example, what I wrote down initially. Let's assume the exponent had been positive. So let's say we're to find the Laplace transform of e to the power of at, positive in this case, then I won't run through the entire computation. The answer will be rather obvious in a moment. So e to the power of minus st dt. Okay, and if we combine this together, that's integral from 0 to infinity of e to the power of, now let me pull out the negative sign, minus s minus a c dt. Okay, I left this negative sign out here because that comes out with the exponent, and if that comes out with the coefficient, if it comes out with the coefficient, our answer is simply positive over here. So I left out that negative sign here. So this obviously should be 1 over s minus a. Okay, so those are some simple examples. Now there are some tables. There's a Laplace transform table that it will do you a lot of good if you just memorize. So for example, let's say we had functions of time and then we're told to find the Laplace transform. We already found that if your function is u is 1. Now I'll write 1 u of t, where u of t, the function u of t, is a function that let me see, how best do I draw this? Let me draw. I'm trying to decide how to draw my vertical axis. I'll draw my vertical axis with dotted lines, and my horizontal axis also with dotted lines. So horizontal axis is my t, and my this is my function of time, f of t, my vertical axis. So u of t is a function that has 0, whose value is 0, as whenever time is less than 0. At the time when t becomes 0, it jumps up to 1, and it remains 1 for time. So in other words, okay, so maybe I shouldn't have bothered drawing this. Let me just simply write it out in mathematics. Okay, this is the best way to define this function. Okay, so u of t is equal to 1 for time t is less than 0. Sorry, is equal to 0 for time t is less than 0, and is equal to 1 for time t is greater than or equal to 0. Okay, so that's my u of t. So u of t is called a unit step function. Unit step function, FCN if you want. So FCN stands for function. So u of t is a unit step function, and it's important to note that u of t, we use it several times in several cases. Okay, so u of t is a unit step function. Bear that in mind. U of t, we generally, in this course, we will generally reserve u of t to refer to the unit step function. Note, it is equal to 1. There are several step functions you can have, but this is a unit step function, so its magnitude is 1, and that 1 starts from the time t is equal to 0. Okay, so if you have that, then the Laplace transform of that is simply 1 over s. If we have our function as e to the power of at, let me put a negative sign there, e to the power of minus at u of t. Now, when I say a function is e to the power of minus at u of t, well, first of all, the Laplace transform is 1 over s plus a. But when I say this u of t, when I multiply by u of t, if you multiply, it means that at time t is less than 0, I am multiplying this function by 0. In other words, any function, say if I have a function, where do I write this so I don't mix anything up? If I have any function and I call that function f of t, let me say f of t u of t. If this is a function here, then it means this function at time t is less than 0, this function is equal to 0. When t is less than 0, this function will simply be equal to 0. Whereas when t is greater than or equal to 0, then this function is simply equal to f of t. So whenever I multiply any function by u of t, it means it has a value of 0 for time t is less than 0, and then it has a value greater than or equal to it has a value of f of t when t is greater than or equal to 0. Okay, the third example we picked in this particular video was e to the power of at u of t, and that is 1 over s minus a. Okay, so there are several other time functions that we have. For example, we could have our sine omega t multiplied by u of t, and the Laplace transform for this is 1 over s squared plus omega squared. Sorry, this should be omega over s squared plus omega squared. And you have cos omega t u of t giving us s over s squared plus omega squared. I mean, all of these could be, you could verify each one of these, just run through the integral. Yeah, you could verify each one of these. Okay, so now there's a Laplace transform table, and I'll refer you to the textbook. Go to the textbook we're using. Remember, we're using Norman Nice. I recommend that you use at least the 2013 edition, the edition that came out in 2013, at least that edition. But whatever the case, whatever edition you use, you will find the Laplace transform table in there. I'll recommend that you go in and take a look at the Laplace transform table. There are several time functions you have in there and several rules you have in there. Because of those rules, you don't have to derive your Laplace transform each time. So that'll be it for this video. See you in the next one.